Okay, guys, today I just want to do a quick lesson to kind of review molar solubility, what it is, but then actually show you a couple calculations that we can do. Once we know the molar solubility of the compound, once we figure that out, what types of calculations are we going to do with that number, okay, or with that value, or what can we figure out? So a couple calculations using molar solubility, so actually using the value of molar solubility for a compound to do some other calculations with it, how we do that. And then also I want to talk about something called the common ion effect and what that does to the solubility or the molar solubility of a compound. Okay, so let's get into it. All right, so last class we talked about our KSP shortcuts, right? And depending on the ratio of cation and anion, we have KSP equals x squared, KSP equals 4x cubed, KSP equals 27x to the fourth, KSP equals 108x to the fifth, right? And if we had a 1 to 4 ratio or 4 to 1, we could figure out a KSP shortcut for that if we needed to. And remember, these are all figured out making a race chart for the compound dissolving in water, getting the equilibrium concentrations of the ions in terms of X, plugging them into the KSP expression, and just simplifying it, right? So like if we made a rice chart with this compound dissolving in water, magnesium sulfide, at the end, we would get at equilibrium, the magnesium concentration is X, the sulfide concentration is X. So if we plug them into the KSP expression, we get X times X, and we simplify that as X squared. Okay, so the same thing would happen here if we were looking at magnesium chloride or potassium oxide, but it would end up simplifying to this ratio. And what we need to understand is when we do that, when we make a rice chart, when we get our equilibrium concentrations in terms of X, and we plug them back into the equilibrium expression, in this case, plug them back into the KSP expression, if we can solve for X, meaning if we know the KSP value and we solve for X, X will represent the molar solubility of the compound. Now, a lot of times X represents other things as well, okay? But in this case, the important thing is if you are using one of these KSP shortcuts, when you solve for X, X will be the molar solubility of the compound. And what that means is how many moles of that compound will be dissolved in 1 liter of solution to make the solution saturated or to make the dissolving process have reached equilibrium, right? That's what molar solubility is. It's how many moles of a salt can dissolve per liter of solution, and that's going to be your saturation concentration of the salt. Okay, and remember, those values will change as temperature changes. So the KSPs change as temperature changes, and so will the molar solubilities. So, we're assuming right now, we're at some temperature where KSP equals this, then I can calculate molar solubility using one of these shortcuts. All right, so let's get into, once we calculate the molar solubility, what can we do with it? All right, so we can answer this question. All right, so let's look at this question. It's asking what mass of silver chloride must be added to 3 liters of solution to make it saturated. So I want to know what mass, how many grams of this do I have to add to a 3 liter, let's say, volumetric flask. So when I make my final 3 liter solution, the solution is saturated with silver chloride. All right. And all we're given is the KSP. And so, let's just assume, this is true at 25 degrees Celsius or something, all right? So we want to make a saturated solution of silver chloride at 25 degrees Celsius. We're given the KSP at that temperature, and the volume of our volumetric flask we're making the solution is 3 liters, all right? Well, what will we do? How could we calculate how many grams? The key is we got to find the molar solubility. How many moles of this per liter? And again, if we know how many moles of a compound we need per liter, then it's an easy conversion to get grams per liter because we can calculate the molar mass of the compound. All right, so it's not a hard calculation. We just got to know what we're looking for. So we're given KSP. We know the ratio 1 to 1. We can go to the KSP shortcut and solve for X. So we plug this value in for the KSP. We set it equal to X squared because it's a 1 to 1 ratio. And when we solve for X, this is the number we get. Now, what does that represent? How many moles of silver chloride for every 1 liter? So we can use this as a conversion factor. Think dimensional analysis. This many moles of AgCl for every 1 liter, or we could flip that and say 1 liter of solution for every 1.3 times 10 to the negative 5 moles. Okay, either way, we can use molar solubility as a conversion factor to convert from liters of solution to moles of solute, or from moles of solute to liters of solution if we need to. In this case, we're going to use this, the molar solubility, to convert from liters to moles. All right. So again, if you go back to the question, we want to know how many grams for 3 liters. Well, this is how many moles for 1 liter. Okay. So here's our calculation. We take our 3 liters, the volume of our solution, we multiply it by the molar solubility that we just figured out, and that'll give us moles of silver chloride, and then we multiply by the molar mass of silver chloride, which we can calculate using our periodic table. All right, 1 silver, 1 chloride. All right, and so we get our answer. All it takes is 0.0056 grams of silver chloride to make a 3 liter solution saturated. That's it. So what is that? 5.6 milligrams. So if you took 5.6 milligrams of silver chloride and you dissolved it in, or you added it to a 3 liter solution, that solution would be saturated in terms of silver chloride. Okay? And again, what is this right here? That's the molar solubility, and we got to remember, what is molar solubility? It's molarity, it's moles per liter. All right? And so we can use it to convert from volume to moles or moles to volume, depending on what the question's asked. All right, so let's go to another example here. All right, this one says, how many liters of a saturated solution of calcium hydroxide would be required to obtain 5 grams of the salt? So we want 5 grams of calcium hydroxide, but our source of it is a saturated solution of calcium hydroxide. So we need to know how many liters of calcium hydroxide solution are we going to need to get 5 grams of the salt. And if we look at the KSP given, that's a very low KSP, so this is not very soluble. So that means a saturated solution of calcium hydroxide doesn't have much of it. So it's probably going to be a large volume. We're probably going to need a lot of liters of this solution to get just 5 grams of the salt. But let's do the calculation, all right? So again, given KSP, we can find the molar solubility, but we got to notice the ratio. This is a 1-to-2 ratio, so we can't use this shortcut, KSP equals x squared. What we have to do is use this one with the 1-to-2 ratio. It's going to be KSP equals 4x cubed. We'll plug the solubility product we were given into the KSP, and we'll solve for x. Okay, so we'll get 2.32 times 10 to the negative 7 moles of calcium hydroxide for every 1 liter of solution. Right? That's what molar solubility represents. That's how many moles of calcium hydroxide of this salt will be in every 1 liter of solution. So we want to know how many liters of the solution do we need to get 5 grams. So it's basically the same type of setup here, but instead of starting with liters, we're starting with grams and we're going to liters. This one, we started with liters, used our molar solubility and got to grams. We're going the opposite way. We're going to start with grams and we're going to use our molar solubility to get to liters. All right, so let's see how that setup looks. We would take our 5 grams of calcium hydroxide, we would divide by the molar mass to see how many moles of calcium hydroxide we needed. And then this is where we would flip the ratio. Again, this is this many moles per 1 liter, or 1 liter over that many moles. That's what we would do here. Moles would cancel out and you'd be left with liters. And look at that, we're going to need almost 300,000 liters of a saturated calcium hydroxide solution to get 5 grams of calcium hydroxide. So not a very efficient way to get our 5 grams of calcium hydroxide, but that's what it would take. If all we had available was a saturated solution of calcium hydroxide and we wanted to get 5 grams of that compound out of it somehow, we would need almost 300,000 liters, okay? But again, I'm just showing you, once we have the molar solubility, what are some questions you might be asked? And these are the types of questions that can be asked once you know the molar solubility. So if you're asked a question like this, your number one goal is going to be figure out the molar solubility and then know what you can do. Okay, molar solubility is a conversion factor to convert liters of a saturated solution to moles of solute in that many liters, or it's used to convert moles of solute required to how many liters of solution you need to get that many moles, that kind of thing. All right. All right. So those are calculations you can do with molar solubility. Now I want to talk briefly about common ion effect. Okay. So this one's, I mean, it's a pretty self-explanatory thing, I think. But salts, so ionic compounds, are less soluble in the presence of a common ion. So let's understand what that means. So what we're saying is, let's say I'm dissolving potassium chloride. You can dissolve more potassium chloride in pure water than you can dissolve it in a solution that contains sodium chloride. Okay, so if I was dissolving potassium chloride into pure water, I'm going to be able to dissolve more. It's more soluble in pure water than it is if I dissolve it in a salt solution. And the reason that is this solution that I'm dissolving the potassium chloride in already has chloride. That's the common ion. So when a solution, if you're taking an ionic solid and you're dissolving it in pure water, then it's business as usual. But if you're taking an ionic solid and you're dissolving it in a solution that contains another dissolved ionic salt, if one of those ions in the solution is one of the ions in the salt you're trying to dissolve, the less of that particular compound you're going to be able to dissolve. So if I already have a solution of sodium chloride and I try to add some potassium salt to it, potassium chloride, I'm not going to be able to dissolve as much of this in that solution than I can in just pure water because you already have chloride. So less of this is going to have to dissolve to reach the point of saturation to get to the equilibrium position, which is the KSP of the salt, when you already have chloride dissolved. Okay, so what you want to be aware of is if you're dissolving it in pure water, distilled water, then business as usual, you can use your KSP shortcuts to find molar solubility. But if you're dissolving in the presence of a common ion, we got to pump the brakes a little bit. We got to watch out. Oh, hey, there's a common ion, chloride in this case. What do we do? It's a little bit more complicated, but I'll show you what we can do. All right. So the molar solubility of a compound decreases if a common ion is already in solution. So let's understand. If I calculate the molar solubility of KCl, let's say I was given the KSP of KCl, I could calculate its molar solubility, and that would be in pure water. But the molar solubility of KCl in a salt solution and in a sodium chloride solution, that's going to be less than the molar solubility in pure water. So the molar solubility of a compound is less in the presence of a common ion than if it was dissolving in pure water. Okay. All right, so let's just kind of review here. All right. So this is just asking, what is the molar solubility of magnesium chloride in pure water? Okay, so pure water, distilled water, in just water, we're given the KSP of magnesium chloride. This is when we can just use our shortcut. So because it's a 1:2 ratio, we can say KSP equals 4x cubed, solve for x. So this is how many moles of magnesium chloride will dissolve in 1 liter of a pure water solution. Okay. Now if we go to number, so 0.0039 moles of magnesium chloride per every 1 liter. Okay. But if we look at this question, this is asking, what is the molar solubility of magnesium chloride in, not pure water, in a 0.1 molar solution of sodium chloride? Okay, so we can't use our shortcut. We can't say KSP equals 4x cubed, and I'll explain why in a second, or you'll see why in a second. But we can only use this shortcut to find molar solubility if we're in pure water. So what do we do if we have a common ion? So we have to recognize, like, hey, wait a minute, I'm dissolving magnesium chloride in sodium chloride. We have a common ion. We have chloride. All right. So how did we get this shortcut? That's what I want to make sure we understand. How do we get this shortcut? We got this shortcut by making a rice chart, finding our equilibrium concentrations in terms of x, plugging them into the equilibrium expression, and simplifying. And whenever you make a rice chart and get your equilibrium concentrations in terms of X, and then you plug those into the expression and you solve for X, if it's a KSP equation, if it's a KSP, then X is the molar solubility no matter the situation, okay? We just can't run to this shortcut for a common ion question. But we can follow the same process. We'll make a rice chart, we'll get our equilibrium concentrations in terms of X, set it equal, plug it into the expression, set it equal to the KSP, and solve for X. And the answer will be our molar solubility. The other thing to note is we should be expecting a number smaller than 0.0039 because this is the molar solubility in pure water, and we know in the presence of the common ion, the solubility of magnesium chloride will decrease. So it's going to be a smaller number than 0.0039. All right, so here's how we make the rice chart. And this is the difference. If it was pure water, this would be 0 and this would be 0. So at equilibrium, this would be X and this would be 2X. And that's how, when we plug it into the expression, we get 4X cubed. But that's not going to be the case in the presence of the common ion. So we're still talking about this equilibrium process. We're talking about dissolving magnesium chloride. So we're talking about this process. But note, the initial concentration of magnesium is 0 because none of this has dissolved yet. But the initial concentration of chloride is not 0. We already have 0.1 molar chloride in there. Okay? So this is 0, this is 0.1. The reaction still has to shift this way to reach equilibrium. We need some magnesium ions. So it's plus X and plus 2X. But at equilibrium, this will be X, and this will be 0.1 plus 2X. But again, if we solve for X, X is our answer. It's our molar solubility to this question, all right? So we plug them into the expression. So here's our expression. We know KSP equals the magnesium concentration times the chloride concentration squared. We know what that KSP number is, 2.3 times 10 to the negative 7, okay? And then we plug these in to the expression. So we say X times 0.1 plus 2X squared, all right? Now what you're saying is, if I want to solve for that, we could maybe use, we're probably going to have to graph to solve for X there. And I know what you're saying, you're never going to have to graph to solve for X. And that's true, because we're going to make a simplification. What we have to understand is that the reaction must shift this way to reach equilibrium. But we know, even if these were 0 and 0, the reaction is not going to shift that far because KSP was a really small number. So the equilibrium constant is a really small number. So only a little bit of this will dissolve. That's what that's telling us. So this X value, even double it, even 2X over here, is really small. And it's going to be really small compared to 0.1. So 0.1 plus 2X is essentially just 0.1. So we're going to simplify that. We're going to get rid of that 2X because 2X is going to, like, if I actually included that, I would get a number like 0.10001 or something like that. 0.10003 or something like that. And that's essentially 0.1. So we're just going to call it 0.1. Okay, and we call this the 5% rule. If what we're adding, if X is less than 5% of the number we're adding it to or subtracting it from, in this case, we're adding it to, we can get rid of that part of the expression. So we're going to simplify that. We're going to get rid of that, and then we get this, okay? 2.3 times 10 to the negative 7 equals X times 0.1 squared. So we make that simplification, and now it's really easy to solve for X, and we get 0.00023, or 2.3 times 10 to the negative 5 moles per liter. So that's the molar solubility in a 0.1 molar solution of sodium chloride, okay? Notice this is a lot smaller than that. This was how soluble it was in pure water, and this is how soluble it was in the presence of 0.1 molar common ion, okay? And notice the molarity went down, or, you know, the solubility went down, all right? So, so let's make sure we understand that. If you're trying to find the molar solubility of a compound, of an ionic solid, but it is not in pure water, and there is a common ion already dissolved in solution, and you want to, again, find the molar solubility of the compound, make your equilibrium, make your Rice chart, get your equilibrium expressions in terms of X, plug them into the expression, like we did here, plug them into the expression, and then you're going to remember, use the 5% rule to simplify, solve for X. That's what you do. X is the molar solubility, always, when you're making a KSP Rice chart. So if it's pure water, just go to your shortcuts. Save yourself some time, okay? And you just use the shortcuts. But if it's not pure water, if there's a common ion, take the time to make the Rice chart and follow the steps. X still marks the spot, right? X is still the molar solubility. And we should understand what to expect. If we knew the molar solubility in pure water, we know in the presence of a common ion, it's going to be less. It's going to be a smaller value than before, okay? So, yeah, that's all I wanted to talk about. So hopefully that helps you with some of the calculations for your homework and helps you prep and get you prepared for our test, okay? So keep working, and I'll see you next time.